Today we're gonna make some tasty donuts with Toroidal Coordinates System and p5.js. This video is a sequel of those two videos about the polar coordinate and spherical coordinate system. In case you haven't touched the other coordinate system besides Cartesian, I recommend you check those first. That's gonna make you much easier to understand this video. So I'll put those links in the description below. So rest of you, let's get the ingredients. To draw a donut in programming, we need to figure out the XYZ components of arbitrary points on the surface. In order to do that, first we consider this ellipse that we see when we cut out the donuts. I define the radius as R1. Secondly, we consider another ellipse here that shapes all over this torus shape, then define the radius as R0. And if I draw a vertical segment from this point P to xy plane and define this angle as phi, then the length is gonna be R1 sine phi. Okay, because according to Sokatoa, this vertical segment is opposite of this R1. You see that? So it's defined as hypotenuse times sine of the angle. Okay. Whereas this segment is adjacent, so defined as times cosine phi. Next, if I define this point as p dash, then the length from the center to this point become like this. I just add up those two, right? And I want to project this segment OP dash on x and y axis, like this. Also define this angle as theta. Then this segment gonna be this segment is opposite of the segment OP dash, so defined as OP dash times sine theta. Whereas this one to be adjacent, so it's defined as OP dash times cosine theta. Did you get that? So at this moment, we already figured out all the parametric equations. This vertical segment is z value here, and this is y, and this to be x, right? But in p5.js environment, the 3-axis is flipped like this. They set x-axis horizontally, y-axis vertically, and then z-axis for depth, right? Hence the parametric equations also should be replaced like this. Now the vertical segment is y. And this horizontal one is x. And this one to be depth value, I mean z value. Okay? I know it's a bit complicated, but I hope you get that. So from now on, I bake the donuts with these flipped 3 equations. So this is my blank oven. I mean sketch, but I already set some properties. First, I set the angle mode to degrees. At default, it's radians mode, it's no problem, but for now, I set degrees mode to make it easy to make sense for many people. And I set the color mode to HSB for convenience. Then set the stroke and the background to my favorite colors. So let's write the donut recipe here. That's beautiful, isn't it? So we already baked one donut in p5.js. At here, I made a 2-dimensional loop to go through theta and phi. Okay, then I draw a vertex at every 10 degrees of the two angles. Then I copy the formula here, set the two radius I define here. This is a pre-made function of the p5.js for mouse control in this 3D space. So we can rotate as we like this. It's very handy. You can try once. I'd like to add some static rotation. Oh, let's also add some animation. I declare a variable offset, increment at here, then add to the fee. So what happened? Yeah, I love it. I want to make sliders to change some values dynamically. So firstly, let's make those two radius interactive. Okay. It's purely fun, isn't it? Okay, so p5.js has pre-made functions to create HTML elements like those slider, div, button, selector, pretty much anything. It's very convenient. If you haven't ever used those functions, I recommend use those here. Then at here, I assign the slider values to those two radius. Then display current slider values at here. Interestingly, when we set the radius 0 to 0, we get a sphere. Okay? Actually, those parametric equations are identical to spherical coordinates when the radius 0 is 0. Yeah? Let's also make sliders for the theta and phi maximum values. Okay, so first theta go around here like this. On the other hand, phi shapes this ellipse. Okay, with those sliders we can make sense much easier. By the way, I worked on some CSS for this background and these sliders to make it a little bit more looks tasty. So I want to apply on those elements, okay? I already made a CSS file here. This top one is for the background of the HTML page. And second one is for the text. And this one is for sliders. This is for the slider handles. Here, okay? And if I uncomment this, it's immediately applied like this. But for rest of those three classes, I have to work on a little bit. In p5.js, there are also functions to set a class or ID for those HTML elements. In this case, I made 3 classes, so I write okay, now it's connected to those classes. Okay. I love it. Now it looks more tasty, isn't it? Oh, I actually intend to display the text above those sliders, so I need to change a little bit. I need to change this order. I set divs above the sliders. I'm gonna show you another recipe of the donut. It's a little bit different, but it's very interesting. So let's separate this recipe into a function. And I make a new recipe, name it Toroidal Spiral. This time I only made one loop for a theta, then replace those phi with the theta. Nothing interesting. Well, I'm showing you this on purpose. We got this figure because we only have the theta loop at here, and we assign the theta not only here, but also here, right? So what's happening is, while this angle, this theta go around 360 degrees, actually this angle is also moving 360 degrees, since we assigned the theta at here, which is originally the phi, right? So that's why we see this kind of gentle undulation. So what I want to do now is multiply those three theta by arbitrary value. Like, let's find out by 6. Yep. Yeah, this is what I want. We got this spring-like shape. But it's too edgy, so I set the density like crazy high, like 0.2. Okay. So what it means by multiply 6 is, while this angle goes 1 time, actually this angle goes 6 times, like this. Where I show you this. Did you get that? For now, I comment out this normal torus. Looks good. Okay. What if instead I multiply those 2 theta instead of this 3 theta? What it looks like? Okay. This time it draws spring-like shape in this way, because this time, while this angle goes 1 time, this angle goes for now 9 times. Then what if I multiply those 3 theta while keeping multiplying this side? This happened. It looks really interesting. Okay, so for now I set 4 and 2, which means while this angle goes 2 times, this angle goes 4 times, right? But it looks identical when the 2 values are 2 and 1. Yep, I just reloaded it, but looks identical. So the shape is responsible to the ratio of the 2 values, okay? I personally somewhat like 30 and 7. It looks beautiful. No, it looks delicious, isn't it? This figure is called like Toroidal Lissajous curve, so I separated it from Toroidal Spiral. By the way, Lissajous curve is a set of mathematical patterns appear when we multiply frequency of the angle in polar coordinates or spherical coordinates. It actually looks very fancy, so I'll put the 2 videos I explained those stuff in the description. I'm gonna show you one more tasty donut using toroidal coordinate. This time I copy from the normal torus. I name it like Bumpy torus. I make a set of terms. There are 2 sine functions here. Then multiply the radius 1 by that. So let's see what's gonna happen. Yeah, what do you think? Now you feel hungry, isn't it? Oh, at this donuts, I'd like to add the animation. Looks more organic now. At every vertex of these donuts, the radius 1 is multiplied by this. So let's check how each term of these are affecting. Did you get that? Well, actually, the left sine function is responsible for the vertical undulation here. And the right one is for the horizontal one that we see from the top, this undulation. And here we have phi and theta here, so hold this term. The value is affected by each location of the points. I mean the vertex, okay? Oh, maybe I should let you see this. I actually deleted one of them. If I delete this one, now the vertical undulation has gone. Whereas when I delete this one, yeah, this time the horizontal one has disappeared, right? And you realize that the number of this undulation is corresponding to this integer. I cut out the donuts. Here now we have 1, 2, 3, 4, 5 undulation is identical to this integer. So if I set like 4, now we have 4 undulation. I set for now 7. Now we have 1, 2, 3, 4, 5, 7. We see 7 undulation. On the other hand, this integer is responsible for the size of the donut, along with R1. And this floating number is for amount of the bumpiness. If I delete those two, the shape is gonna be like this. Because at this moment, the value range of this bump is -1 to 1. Because now we only have the 2 sine function here, right? So the whole radius gonna be for now -80 to 80. So we add 1 here. Now the range is gonna be 0 to 2. So the whole radius is gonna be what is it? 0 to 160. But because the bumpiness is too much, we multiply by the small number, like 0.2. So that the amount of the bumpiness will be reasonable. Alright, so thank you for sticking with me so far. Actually, there are lots of other tasty donuts exist that we can cook with Toroidal Coordinate System. But I think that's too much for this video, so I'll explain detail in another video in the future. I'll see you in the next video. Yeah, that's good. Just not as much as the donuts we just made.